This is Cameron McCormick from Mozilla, and he's going to be talking about the Web IDL specification.
That's right. Thank you, everyone. Before I talk about Web IDL, though, I'd like to talk a bit about the DOM. So the DOM was first published in 1998. DOM is the document object model, so that's an API to access the tree of nodes within an HTML or some other markup document. I think Dirk gave a good introduction to basically what that is before. And so when the first version of the DOM was published in 1998, it was actually the first web specification to use an IDL language to specify the API that it's defining. So the authors of that specification chose OMG IDL. So if you're familiar with the OMG, which is the Object Management Group, they worked on a system called Corba, which is some sort of remote RPC kind of thingo. So they chose that because I think it was basically the main IDL language that existed. And this is kind of what it looks like. So here's a snippet from the DOM specification defining the node interface. So the four main parts we've got here is the interface node bit, which introduces the name of the interface. We have a couple of constants here. They have particular type and value and name. There are attributes, which are basically correspond to like properties or fields on the object that you can set and get. And they have particular type and name as well. And operations, which is just sort of IDL speak for methods on the object. So interface definitions look like this, and the IDL language has a bunch of C-like types like float, bool, unsigned long, and so on. So the advantage of writing these interfaces using an IDL language is that you've got language independence. So this is meant to be sort of abstract language, and then you have particular concrete implementations of the APIs in particular languages. And the DOM was designed with two target languages in mind, Java and JavaScript. Now we all know where Java went on the web platform, which is basically nowhere. So JavaScript is really the main one that we're interested in now. Unfortunately, OMG IDL didn't define a particular mapping to JavaScript. So even though OMG IDL is used in the specification, OMG IDL doesn't define how these IDL snippets map to JavaScript. So to overcome that, the authors of the DOM specification included some appendices to define how it should map to Java and JavaScript. So unfortunately, these appendices were not particularly precise. And the one thing, or the two things you really need for interoperability between browsers is precision and accuracy. So before I show some snippets from the specification itself to show where some of these problems come up, I'll just give a short primer on some JavaScript fundamentals. So JavaScript has a few primitive types like Boolean, number, and string, and it has objects. So objects can have like key value properties on them, arrays are objects, functions are objects, regular expressions are objects. And the thing common to all of these kinds of objects is that they have a set of properties on them. So in JavaScript, well, in the 5th edition of ECMAScript, which is the standardized name for JavaScript, a property has a string name, and it either has a value or it has a pair of functions to get and set the value of the property. So the one with the value is called a data property, and if it's got to get a set of pair, it's called an accessor property. And internally, properties can have these three different attributes as well. They can be writable or not, which controls what happens if you try and assign to the property. It can be enumerable or not, which controls whether it will appear if you do a for loop over the object. And they can be configurable or not, which means you can, if it's configurable, you can change any of these attributes and what the getter and setter are, and whether it's a data property or an accessor property. And also JavaScript objects have prototypes. So prototypes are used as a sort of simple inheritance mechanism. So each object has one other object or no other object as its prototype that it inherits properties from. So if you have an array instance which might have properties itself, being 0, 1, and 2 for the array indices and a length property, it inherits from the array prototype object, which has functions on it like push and pop that are suitable for all array instances. And the array prototype object inherits from the object prototype object, which all or most objects inherit from. And that has some very generic functions like toString to control how an object gets stringified. So let's have a look at some snippets from the actual JavaScript binding appendix from the DOM specification. This is the old DOM1 specification. So for a constant, it says this. The node class has the following constants, node.elementNode, and it says the constant is of type number and its value is 1. Now one problem that stood out to me when I was reading that is that, well, JavaScript doesn't have classes and it doesn't have constants either, at least in the versions that are appropriate here. So it's really not being clear about what particular JavaScript constructs the IDL constants are meant to correspond to. And secondly, if you actually try in browsers, you'll find that these constants, like element underscore node, are actually visible both on the node constructor, so the capital N node, and also through node instances as well. So you can say, like if you have like document, for example, is the document node, you can say document.element node and you can still access that constant. So the appendix also doesn't say where exactly, well, it doesn't say that it should live in both places, but empirical testing shows that it actually needs to. For an attribute, here we have the wording for the node value attribute, and it says the properties of type string and can do some things with exceptions if you try and set bad values on it. So firstly, what does it mean for a property to have a type in JavaScript? Because that doesn't really make sense either. Values have types in JavaScript, but properties can take on values of any type. There's no strict typing in JavaScript. So what does it really mean to say that the property is of type string? What does it mean if we try and assign a value of a type other than string to that property? So here we have trying to assign a number to it, or trying to assign an object to it, which has a custom way of stringifying the object. What's meant to happen there? Is the number meant to be turned into a string somehow? With what sort of formatting? Should that toString method be invoked on the object when it tries to convert it into a string to assign to node value? So those things are unclear as well. And also it doesn't really say if it's a data property or an accessor property. Accessor properties kind of make sense when you think about these IDL attributes, because when you assign to them, you want some behavior to happen. So when you assign to node value, it's going to change some like text that actually appears in the web page, which you couldn't really do without some magic if it's a data property, which just doesn't have any behavior when you assign a value to it. And those sort of things are actually observable to script as well. So whenever you have behavior that's unspecified, but which would be observable to authors when they write their scripts, that's a recipe for incompatible behavior and people writing scripts that work in one browser and not in another. And finally, here's some wording for one of the operations, so append child. So firstly, well, again, it doesn't say where this property is meant to live. It probably makes sense for it to live on the node prototype, because this same function is usable for all node instances, but it doesn't say that. But it also says the new child parameter is a node object. And what does it mean for that value that expects to be a node object? What is a node object? Well, you've got the nodes that are provided to you by the browser implementation once your document's been parsed. But what if you pass in your own little JavaScript object which kind of looks like a node? We give it a node type property. Is that sufficient for it to be considered as a node? Or what if you try and make it inherit through a prototype chain the actual real node prototype? Does that count as a real node when you pass it in? So all of these questions are unanswered, and various others as well, by the original DOM specification. And unfortunately, all of the web specifications up until about 2008 were basically written by this. So we had like 10 years of unspecified behavior that browser developers have had to reverse engineer each other to see what kinds of things, in what exact ways these properties are meant to be exposed to JavaScript. But because all these specifications use an IDL language, what we should be able to do is define once what it means for this IDL fragment to mean in the actual JavaScript reflection of the API. So that is what we did with the Web IDL specification. So there's meant to be a URL there. There we go. So this is the W3C specification. which I started maybe in 2006, I think, and is still being refined. And basically it has two goals. One is to define all of these undefined things like the examples I showed you. And secondly is to evolve the IDL language so that it's more appropriate for JavaScript APIs. So one of the limiting things about the OMG IDL language is that it kind of gets you into writing Java-like APIs. There's no way to make use of the specific things that JavaScript allows. So we want to be able to expose that in the IDL language so that web specification writers can write APIs that feel natural to use in JavaScript and don't feel like a bunch of Java factory method calls. So let's have a look at the kinds of behaviours that WebIDL does define. So firstly, and maybe most fundamentally, is it defines the type mapping between the types that the IDL language has, like unsigned and short, needs to be exposed in JavaScript as a number value. So JavaScript doesn't have different width integer types, it's only got number, which is a double precision floating point number. So that means we have to sort of define what happens if you have an attribute which is of type unsigned short and you try and assign 1.5 to it. What does that mean? And more generally, that means we need to define how you convert values, JavaScript values, into the IDL types at the sort of more abstract layer. So before we saw the example of trying to assign a number to the node value property, which was declared to be of DOM string type. So basically, WebIDL says that when you convert into a string, you effectively pass it to the global string function and do like whatever the natural JavaScript stringification behavior is. Now, it doesn't actually say call the actual global string function because authors can actually replace that with something else and we want to have consistent behavior. So what it means is that that hex value 10 there actually gets converted into the string consisting of 1 and 6 as the two characters. And for the second one, the object, it says, yes, that toString method on there is actually going to get invoked when you try and convert that object to a string. As for what to do when you pass something when it's expecting an object of a particular interface, like node, basically we decided that, well, you have to have an actual real node that the implementation has provided for you. You can't sort of mock one up yourself. And that's because really behind the scenes, the node object needs to have a lot of sort of internal machinery to be able to participate in the document tree properly, know how to be styled and how to be laid out and so on. And if you just write some JavaScript object, which is, hey, I've got a node type and a node value, and let's insert it into the tree, it's not really clear what that's meant to do. So the simplest thing is just to say, well, we'll just throw an exception if you try and pass one of these values in. So more generally, WebIDL defines what properties, constants, attributes, and IDL operations correspond to and where they live. So where they live on the prototype or on the object itself, what their attributes are, so whether they're writable, configurable. And by doing this, by defining these things in terms of actual language features, it makes the behavior not magical and can help sort of author understanding. You can actually, for an IDL operation which corresponds to an IDL attribute which corresponds to an accessor property, so it has a getter and a setter, you can actually use the standard JavaScript object get property descriptor or whatever it is to extract out those getter and setter functions and replace them with your own if you want to. So that also allows sort of monkey patching of behavior for like libraries that do shims for things where you can replace some existing implementation. And that's because we define it, these properties as being configurable and you can actually modify them. And various other things it defines as well. So what happens when you pass too many or too few functions to too many arguments to a JavaScript function which corresponds to an IDL operation. What happens if you try and apply some function to some other object that it's not expecting. How the inheritance of interfaces corresponds to the chain of prototypes in JavaScript. How DOM objects get stringified, like where you have square bracket object and then some name. And various other things. So they're all sort of defining the existing gaps that we had before WebIDL came along. Now the other part of it was evolving the IDL language to allow more JavaScripty APIs to be defined. So what we're aiming for is for JavaScripty APIs to be able to be defined with WebIDL, but still to have some level of language independence so that if you wanted to, you could map those interfaces into your Java or Objective-C, because there are some people who are interested in that. But obviously the more important part is to have these APIs defined for use on the web where we'll be using JavaScript. So one example of a new feature that's in WebIDL that was not in OMG IDL is indexed and named properties. So if you're familiar with the node list interface, so if you get .child nodes on some node in the DOM, it returns an object which has a list of the children of that node, and it actually exposes those children as sort of array index-like things, so where you can use square bracket 0, square bracket 1. So you can't actually say with OMG IDL how that's meant to be exposed. I mean, it's just not in the language. In WebIDL, we have a keyword getter and a setter one as well that you can tack onto an existing IDL operation to say, well, really, when you try and access an array index property, under the hood, we're going to be invoking the behaviour of that operation there.
Is the word item there key, like a keyword?
Oh no, so that's the name of an operation that already exists. So you can actually say kids.item bracket something as well. I mean, so that's how you would have to use it in some language which didn't have array index kind of exposed things. Another option that you can use now in WebIDL is to define certain interfaces as being constructible. So you can stick this square bracket constructor on there, and you can say new document, which is, I mean, being able to new things is pretty common in JavaScript libraries, so it makes sense to be able to define APIs now to use that functionality. Another one is dictionaries to allow, I'll just skip over this quickly, to allow sort of named arguments to be passed into methods as well. So if you're familiar with DOM events, you can get some really long initialization methods with like 5 booleans in a row and you don't know what they are. So this makes them sort of more readable APIs. And I'll skip some more things there. Okay, so in terms of implementation, in Firefox we have been recently converting our underlying bindings from JavaScript to C++ to use WebIDL directly. So previously we had some other IDL variant language. And really that means that firstly it's easier for developers because they can just copy and paste IDL fragments from the specification and just paste them into a file and it'll generate the right bindings for us. It's also easier to write the C++ classes that implement the interfaces because their old IDL mechanism had some weirdo things like it could support multiple inheritance and you'd have to cast between lots of objects and it was quite difficult to use. And thirdly, and maybe most importantly, the generated code is actually a lot simpler and faster. So in terms of performance, so this is the performance of the actual time doing the bindings code, which is like all the time between calling the JavaScript function and getting into the C++. So that's looking at the JavaScript arguments, converting their types, making sure you have enough arguments, a lot about arguments, I guess. So basically, compared to our old standard bindings, which are like the defaults which aren't optimized, the new WebIDL-based bindings are basically 100 times faster. So on a 2.7 gigahertz machine of Boris Spassky's, it took maybe 1 microsecond for the bindings of a very simple IDL attribute to run. And now that's down to like a few cycles, so 8 to 9 nanoseconds. Now we did have some optimized versions of bindings for particularly important things. So these are these quick stubs that I mentioned there. So for really important ones, we're maybe only at best 2.5 to 3 times faster than those customly written bindings that we had before. So you can see the result of that here. I ran this the other day. It's, Dromeo is a sort of common DOM performance testing suite. I'm not sure how good it is. But you can see here that with these particular test suites that, well, the difference between Firefox 18, which is the current release, and 21, which is the current nightly, I mean, most of this difference is going to come from the IDL improvements that we've done, so implementing based on WebIDL. So with some of them, we actually get quite substantial like percentage increases in terms of number of operations that the test suite is doing. Obviously, I haven't actually looked into exactly what kinds of operations they are, but you can see the kind of effects that even like absolute time small improvements for the for the bindings layer, because as I said, it's like before it was 1 microsecond, so that sounds pretty quick. But if you're doing a lot of them, like if you're doing lots of canvas calls, then you want to try to really minimise the amount of work that's going on each time you call a function to like draw a path. Okay, and that's all. Thank you very much.
So you basically got a pretty impressive speed improvement. It also reduced your code size, is that correct? Because it's now generated rather than like before you generate it.
Yeah, that's right. So the default before with the old bindings is that it's also generated but sort of poor performance characteristics. Basically, the old bindings, the standard ones, which is the 100 times slower ones, each function that exists on an object, so like a JavaScript function when you call .append child, doesn't know anything particular about like what arguments it needs to convert to or what underlying C++ thing it's going to call eventually. It does some like sort of runtime introspection on the interfaces that we've declared, and that's sort of where all that extra time is coming from. And the custom ones that we had were like custom JavaScript function objects, like when you call .append child. That particular function object instance knows that it's going to be calling append child very soon, and so it knows exactly which arguments, like how to do the argument conversion and so on. So the thing is, yeah, with the new bindings, the generated code has that knowledge already. So we have that sort of fast behavior by default. So we can get rid of a lot of the custom quick stubs that we've written there. Yeah, so it is going to result in like smaller actual written code size. Yeah.
So what's after the DOM then? What else are you going to do this on?
It depends what you mean by the DOM. I mean, all of the API, like the web standard APIs that are defined that use WebIDL in the specs, I mean, we'll be transitioning them all to use WebIDL eventually. So I think Canvas and a few DOM things like Node and Document and Node List have been converted. And there was just work in the last few weeks, converting a lot of the SVG interfaces as well and some of the HTML ones. So I'm not really sure what the time frame is for all of them to be done, but it's kind of a relatively simple mechanical process as well, a bit of handwork to do. Yeah, so eventually they'll all be converted.
Do you know if something similar is being done in Chrome?
So
WebKit, I should say.
It's a bit hard for me to tell. Every time I ask someone at WebKit, which is maybe like every year or so, they are fine with the stuff that's in the spec, but they might have some implementation-specific concerns about how far. Like one of the major changes in WebIDL versus sort of what the de facto standard was before is having the attributes correspond to properties on the prototype. So before ECMAScript 5, so before we had like accessor properties, properties like .node value were kind of magical objects on the instance itself. So when you look up the property, you didn't have to then search one level up to see the prototype. So I think some WebKit people are a bit concerned that that might result in slower property lookups. I think it's probably just a matter of engineering though to get around that.
You mentioned that you, once auto-generating the bindings, that you have an extensive test suite that you run against them. Has this enabled you to find errors in the definitions themselves, or has it assisted in finding problems in the specification? Or do you think it can?
Definitely. So I think the first thing that the Python script that parses the WebIDL stuff does is like checks that it's actually correct. And many specifications have incorrect WebIDL, like they have syntax errors or they're using types in the wrong way or whatever. And so Boris has done a lot of filing bugs on specs because of that, which is good because we can find problems in the specifications. But yeah, there are problems that come up like that.
Thanks very much.
Okay.